Hey guys, this is the next set of notes for Unit 3. This is on heat of formation. So heat of formation is just another way to find change in enthalpy. Heat of formation is the heat released or absorbed when 1 mole of a substance is formed under standard temperature and pressure. So just as an FYI, the standard pressure is going to be 1 atm, but the standard temperature is 25 degrees Celsius. So the reason it's not 0 like you're used to seeing is because STP for a gas is 0 degrees Celsius and 1 atm, but these for the most part won't always be gases. So we'll use their most stable form, which is 25 degrees Celsius. Okay, so here's an equation. This is giving me the change in heat of formation as negative 289 kilojoules. So that little degree sign tells us that the reactant elements are in their standard states, their most stable form, which is at 25 degrees Celsius and 1 atm. This is usually indicated by the little degree sign after the change in enthalpy with a little F at the bottom. The change in enthalpy and heat of formation of an element in its standard state is going to be 0. The heat of formation for a substance is similar to having its potential energies, which we haven't talked about really, but it's a measurement of how stable or unstable a substance is going to be. So how do we use a table to figure out the enthalpy change for a reaction? So in class, I'm passing out a table with a bunch of heat of formation numbers on there. It is also linked in your slides. So if you're watching this at home, when you come back to class, make sure you ask for one of those charts. The enthalpy change of a reaction is equal to the sum of the enthalpy change of formation values of the products minus the sum of the reactants. So each value for all reactants and products must be multiplied by its coefficient. So if an equation is already balanced, make sure that you use that coefficient to multiply the heat of formation number. We're going to use this equation. So I have the sum of the products minus the sum of the reactants. So let's look at an example. This says to calculate the change in enthalpy for this equation. So I'm looking for change in enthalpy. So I'm going to go ahead and use that heat of formation equation. So I'm going to sum up the products, sum up the reactants, and subtract the two. So I have this kind of written out already. One of my products is sodium hydroxide, and I have 2 of those, so you're multiplying 2 by the heat of formation of sodium hydroxide. That's going to be found on the chart that I'm handing out to you, and we'll do that for all of the compounds. So again, we're going to look at the provided table to find the heat of formation for each one of these substances. So here on my next slide, I already have those filled in and they're highlighted. So all of those highlighted numbers came from the chart. So now I would make sure that I multiplied 2 times negative 469.6. Make sure you multiply all of your coefficients by whatever that heat of formation is. Once you add up all of those answers, you would get your enthalpy for the reaction. So in this case, it is negative 367.52 kilojoules. So some things to note, notice that the table of heat of formation that I give you, it's kind of a combination of several different tables. Some substances could be listed more than once. They could have different values than maybe if you looked one up on the internet. It doesn't really matter. All the numbers are going to be pretty close. So basically our answers might be slightly different, and that's going to be okay. Another example. Calculate the change in enthalpy for this equation. So again, I'm going to use that same equation, products minus reactants. So my products are CO2 and H2O. My reactants are C2H5OH and O2. So when I add up all my enthalpies, or my heat of formations, which you need to find on your chart, I plugged them in, they're highlighted. So again, these numbers might look different than what's on your chart, and that's okay if they're off by a little bit. I actually pulled these numbers from a different chart from what I am giving you in class, so that is why the numbers look slightly different than what you see on your table. So when I multiply my coefficients and then add everything together and subtract, I would get negative 1367 kilojoules as my final answer. Okay, if you are in class, we will be working on the lab. For quarantine students, I haven't figured out what I want you to do yet for the lab, so hang tight and I will let you know soon.